Hello students, we are going to look at class exercise 3, chemical bonding. Right, so this question requires you to make use of the VSEPR theory. So over here is VSEPR theory to explain why the bond angles in the molecules are as follow. Right, so we can group them into two separate categories. NF3 ammonia in one category and then BF3 in another category. Okay, why do we do that? Because if you try to draw the dot and cross diagram, right now I'm sure you can do that quite easily for these three simple molecules. You'll notice that for NF3 and ammonia, right, the two of them have 4 electron groups around them. Okay, 4 electron groups around them. BF3, you only have 3 electron groups. So leveraging on this, when you are trying to explain how we get the bond angle that is being shown to us, what we need to do will be to look at the first principle of VSEPR theory, or the first assumption, that is electron groups or electron domains will arrange themselves as far apart as possible around the central atom. So for 3 electron groups, the best arrangement will be trigonal planar. So that will take on an angle of 120 degrees. Yeah, so that explains why BF3 is symmetrical and it has a bond angle of 120. Yeah, so that would be the simplest to explain. So I think one way to go about doing that is to get BF3 out of the equation first, and then we try to explain the remaining two. Okay, then with that, you can move on to explain NF3 and ammonia. For NF3 and ammonia, both of them have 4 electron groups, of which one of it is a lone pair of electrons. So if you use ammonia as the benchmark, okay, if you use ammonia as a benchmark, remember that for 4 electron groups, there are 4 benchmark molecules that you might need to be aware of. Methane, ammonia, and water. Okay, so methane 0 lone pair, ammonia 1 lone pair, water has 2 lone pairs. Yeah, so if you go across, the bond angle is about 109.5 degrees, about 107 degrees, and about 105 degrees. Yeah, why is it that it decreases in this particular order? The reason is because of the second assumption of the VSEPR theory, that is lone pair repulsion is more significant than lone pair bond pair repulsion, which in turn is more significant than bond pair repulsion. Yeah, so because of this, we are expecting molecules with 1 lone pair in 4 electron groups to have a bond angle that is slightly smaller than 109.5 degrees. Yeah, so if there are no other references you can make, then we will quote the bond angle to be 107 degrees. And ammonia, in this case, happened to be the reference. So we give it a bond angle as 107 degrees. Yep, but in our case here, we are supposed to compare between these two. So we are supposed to compare between NF3 and ammonia. Why is it that NF3 has a smaller bond angle than ammonia? So in that case, we have to look at a factor that is outside the VSEPR theory. Yeah, so basically the VSEPR theory will give you a generic bond angle like what we have discussed. Right, so 3 electron groups, we are looking at trigonal planar geometry, 120 degrees. 4 electron groups, we are looking at tetrahedral geometry, 109.5 degrees. Yeah, any variation in that, then we need to look at the number of lone pairs. Yeah, so 1 lone pair, we are looking at lone pair bond pair repulsion, more significant than bond pair repulsion. So eventually it will take on an angle 107. 2 lone pairs, like that in water, we are looking at lone pair repulsion, more significant than lone pair bond pair repulsion, which in turn is more significant than bond pair repulsion. So that will take on an angle of 105 degrees. Okay, if they share the same number of lone pairs and bond pairs, like in the case of NF3 and ammonia, then what do we need to do now? So right now we need to look at factors beyond the VSEPR theory. Okay, so if you look at the atom that is bonded to N for NF3 is actually fluorine. So fluorine is actually the extreme case we are looking at. Okay, so when we try to draw NF3, it will look something like this. F is here, F is here, and F is here. Okay, then we will contrast this with ammonia, with a lone pair here, H, H. Okay, if I represent the lone pairs of, sorry, if I represent the bond pair of electrons, okay, with two crosses. So I'm going to expect in ammonia, the crosses are actually nearer to nitrogen. Why is that the case? Because between nitrogen and hydrogen, nitrogen is more electronegative as compared to hydrogen. So I will expect the electron pair or the bonding electron pair to be closer to nitrogen. In contrast, for NF3, fluorine being more electronegative than nitrogen, I expect the bonding electron pair to be further away. Okay, yeah. So if you look at both situations, now that I draw them side by side, you will notice that the bonding electron pair in ammonia is actually closer to the central atom as compared to that in NF3. So when you take this into consideration, that means that the bond pair repulsion around the central nitrogen atom in NF3 is weaker than that in ammonia. Yeah, all factors being equal. Yeah, so you notice that when we compare the two, right? The lone pairs is already here, so this is one of the factor that is common between the two. So now we're looking at bond pair repulsion in NF3 being less significant or weaker than that in ammonia. And that explains why the bond angle is smaller than the usual 107 degrees. In fact, if you try to Google it, the actual bond angle is 90-ish degrees. Yeah, so it's not really 102. Yeah, but again, we are working on these questions as it is, assuming that everything, or all the information given to us is correct. Okay, so I'm going to move on to 1b. So with 1b, we have antimony in group 15. So it forms a series of salts. Okay, so it has a charge of N minus. Very important data given here, so you need to take note of it. It has a square-based pyramid geometry. So maybe I should write in the lone pair first. So there's a lone pair of electrons over here, square-based pyramid. How do we know there's a lone pair there? Yeah, because square-based pyramid belongs to 6 electron groups with 5 bond pairs and 1 lone pair. So drawing in the lone pair there helps a lot in deciphering the final charge or even later on the oxidation states. Yeah, so that's a very important thing that you need to be aware of. Some of the students might not be aware of this particular representation, like what is this hash line and what is this bolded line, right? Okay, so the hash line is often used in organic chemistry, showing the projection of the atom in space away from you. So if you imagine that the plane of the paper is where the bond SBF lies, right? You can imagine that the fluorine here is actually projecting into the plane of the paper. Okay, so these two fluorine projecting into the plane of the paper directly away from you. And then these two fluorine projecting out of the paper directly towards you. If antimony is at the same eye level as you, so F will be directly away and the other F will be directly towards you. Of course, towards you, it will be at an angle. Yeah, so I think you can try to visualize it. Okay, so it's like a square-based pyramid with the tip pointing towards you. Now you turn it 90 degrees and then with the 2F towards you and the other 2F away from you. Okay, so with this in the picture, now we're supposed to deduce the number of valence electrons around antimony. Okay, then around the antimony atom, the value of N and the oxidation number of antimony in this ion. Okay, so if you do a quick count, 5 bonding electron pairs and 1 lone pair. So the total number of valence electrons here will be 12. Okay, what about the value of N? Okay, so this might pose a little difficulty for some students at some point in time. Okay, so how do we attempt this question easily? Okay, so one way to go about doing that is, maybe I zoom in, I just erase this part off, is that we are aware that antimony is in group 15, so therefore it has 5 valence electrons. So that means that in this case, 2 of the valence electrons, it's now part of the lone pair. So there will be 3 more valence electrons being used to form a bond with fluorine. So I'm just going to write it out here. And then for fluorine, I'll put a cross. So this is cross. So this is a normal shared covalent bonds between Sb, antimony, and fluorine. Then the remaining 2 fluorine is likely to exist as fluorides. Yeah, with a negative covalent bond towards antimony. So these 2 will be acting as a F minus. So when you have 2 F minus here, your N will take on the value of 2. Yep, so that is one strategy you can use to solve it. I mean, I thought that would be the simplest, because when you do it this way, it is actually through a logical deduction, like how many valence electrons antimony originally has. Because it's being in group 15, it should have 5, and then therefore the 5 blue dots, and then after you try to distribute it around the antimony center, and then after that you incorporate the fluorine in, and then you realize that 2 of the fluorine must exist as fluorides. Yep. Okay, then oxidation state will be straightforward. What we can do is we let antimony be X. Okay, we have 5 fluorine, so take on an oxidation state of -1, so that's -5, equals to overall charge will be -2. So in this case, antimony will have the oxidation state of +3. All right, next we'll look at question 2. Question 2 follows the dot and cross diagram in exercise 2. Question 1 and 2a. Unfortunately, I don't have the dot and cross with me now. We can actually derive it on the spot as practice, right? Okay, so first of all, we look at NO2 plus. So again, fastest way to solve this, nitrogen has 5 valence. Okay, oxygen has 6 valence, so times 2, we have a total of 12 electrons. The positive charge here means that it might be easier if you consider electrons to be removed from the less electronegative element. In this case, it's nitrogen. So we do a subtraction, -1 equals to 4. So right now, nitrogen has 4 valence, oxygen is 12 in total. So what we can do here is we put the nitrogen in the middle. Okay, just put dot, cross, 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 cross. Okay, make it easier. Then you know that with 2 electrons, that means that it can pair up with another 2 electrons in oxygen, and that will give it an octet configuration. So just nice, so we'll just do that. Okay, oxygen, oxygen. Okay, just do a quick one. And then with that, overall charge plus. Okay, so we'll do a quick check. 8 valence electrons around oxygen, and then another 8 around nitrogen. So that's fine. Okay, yeah, so that would be the fastest way to do the dot and cross. And then to draw the Lewis structure, showing the shape. Okay, so what we're going to do now is right on the right hand side. So double bond O, double bond O. The bond angle will be 180 degrees. So the shape is linear. Okay, we put a square bracket with an overall plus charge. Yep, so that would be the answer to part A. We'll do the same for N3 minus. So again, N3 minus is the tough nuts to crack. Okay, so nitrogen, 5 valence, 3 in total, so we have 15. Okay, with extra electrons here, so we +1 equals to 16. Again, easiest way is to form N2 first. So if we form N2 first, we get a triple bond on the left. Okay, right, so this N2. Then we try to draw another nitrogen in, because if you're going to form a double bond with the last nitrogen, I'm just going to illustrate it in red, we're going to end up with 10 electrons around nitrogen. There is no goal, so we're just going to write it out here. Okay, and then remaining, we just fill it with crosses. So that will be 1, 2, 3, 4, 5. So that's extra 1, 6. Okay, yeah, so this is just nice, square bracket over charge minus. Okay, so in terms of the Lewis structure, there will be a triple bond. Okay, dative covalent bond towards nitrogen. Okay, and then square bracket overall minus. Yep. Okay, so for those of us who look at former charges, then maybe this may not be the best answer, because this will actually introduce -2 former charge to the nitrogen atom on the right hand side. Yeah, so what we can do is we're just going to do the same thing. So I'm just going to put a bracket here. Okay, so I will put cross cross. Okay, and then n, and then cross cross dot dot. Okay, for n here. Okay, then what I'm going to do is I'm just going to shift one of the original electrons in the middle end to the left. Okay, so this will take on cross dot here, because originally nitrogen 5 valence, so 5 crosses with 1 extra dots from the nitrogen in the middle, so that's just nice. And then cross cross, and then cross cross, cross cross. The final cross actually comes with the extra electrons. Okay, so this will be the beautiful structure that we probably, some of you might remember, we went through in tutorials. Okay, so it will, so on the whole, it will look like this. So this might be the better version of the answers if you truly believe in distributing electron densities equally across the system if the condition arises. Yeah, so this might be the better version of the answers. But of course, for assessment purposes, if things doesn't come naturally to you, then the first one will be perfectly fine. Okay, I mean, there's no hard and fast rule what it should be like. Okay, there is also a third answer if some of you recall that we gone through before in tutorials. That might actually be a little bit easier for most of you. So for example, we can keep everything similar. Okay, so I'm just going to redraw this. Okay, so everything on the right hand side will be kept similar. Cross. Okay, so this will be the nitrogen with the extra electrons. Then over here, right, what's going to happen is that I'm going to introduce a dative covalent bond. Okay, from the nitrogen in the middle. Okay, with that, I do not need to switch the electrons around. You know this? So basically, it's just a switch between this and this. Okay, then it might make the situation a bit easier for most of us, because our Lewis structure will end up with something like this, with dative covalent bonds. Okay, and then dot 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 dot. Okay, and a minus. Might be easier for some of us. Really depends. Okay, so all road will lead to Rome. You decide which is the strategy you want to use. Okay, so whatever the case is, the bond angle is 180. Shape is linear. Okay, so you notice that no matter what strategy we use, it will not change the final outcome. Okay, next we look at N2O4. N2O4 is best approached with symmetry in mind. That means 2 times NO2. So if you try to draw the dot and cross for NO2, most of you might know by now that you can't have 2 double bonds, right? So the nitrogen in the middle, no choice, will have to be a single electrons, and then there will be a dative covalent bond towards the oxygen on the right hand side. So with that into the picture, I can complete another dot and cross below. Okay, and then I just repeat the same diagram, and then I'll end up with a diagonal. Right, so in this case here, the shape will look something like this: double bond O, and then dative covalent bond to O, single bond N in the middle, double bond O, single covalent bond O. Okay, so in this case, the bond angle will be 120. So there are 2 central atoms, 2 nitrogens, so both are 120, trigonal planar geometry. Okay, for N2O5, is an expansion. Okay, so we'll do the same thing, except we are going to insert an oxygen in the middle here. Okay, so I'm not going to do the dot and cross, because just repeating it. So you guys can write it on the paper next to it if you want. Okay, so I'm just going to complete answers here directly. So single bond O, okay, and then O here. Okay, I'm going to bend it, yeah, because it has a band geometry around the oxygen in the middle. And then I put the N here, the double bond O here, the dative covalent bond O here. Okay, so in this case, bond angle will be 120 degrees. This angle will be 120 degrees. So this one will use the benchmark that I mentioned earlier on in my illustration here. So we'll use the H2O benchmark, about 105 degrees. Okay, so we'll use 105 degrees. Of course, the bond angle need not be exactly 105. It could be much lesser, it could be more. We are not here to debate. We are just here to predict an angle based on what we know. Okay, the final one, the adduct. Okay, so AlCl3, aluminum center. Again, I'm not going to draw a dot across. You might remember that it has 6 electrons around aluminum center, so therefore it is Lewis acidic. Nitrogen has a lone pair around the N, readily available to donate to a Lewis acidic center, so that makes N Lewis basic. So with that into the picture, we can combine them. Okay, so we draw N here, N here, and here. Dative covalent bond, aluminum center. Then Cl, Cl, Cl tetrahedral geometry. So again, 109.5 degrees. This is 109.5 degrees. So the shape will be tetrahedral. Okay, it must be very specific. Around N and tetrahedral around Al. Yeah, you must be very explicit when you state the shape.